Okay, now I have started recording. So let us continue. Uh, so we were discussing about phase space, and we discussed the example of a simple harmonic oscillator. And there is another important aspect of phase space that you will learn anyway in statistical mechanics. So let me outline that aspect through an example. So the example would be so particle in gravitational field.
Sir,
Yes.
so just one doubt. Uh, is this like the phase space trajectory? Can it be like unclosed? I mean, should it be always a closed curve?
No. This is one of the example where you will see that.
Okay, sir.
Okay. All right. Uh, so, uh, so the way I want to draw this is, suppose suppose this is your q axis, and this is your momentum. So you can think about the momentum as your vertical momentum. So this thing you can think about your pz, and this q is equivalent to your z coordinate, your vertical coordinate. And on the ground level at z equals to 0, you assume the potential energy to be 0. Okay. So then at a height q, the potential energy would be uh, minus mgq. Actually, what I'm measuring from. Let me check. Mm, okay. So suppose I am the particle is falling from a gravity and from a height uh, z equals h, and so this is your ground. So this is z equals 0. Let us put it here. It's not z actually, and you drop the particle from here, and basically here you take your potential to be 0. So as the particle falls, its potential energy decreases. So so this distance you call q. Okay. So then at this point v will be minus mgq if this is your if this is your 0 of the potential. It doesn't matter where you take the 0 of the potential, but in my notes actually I use this convention. So it is not actually z, but it is in the z direction. It's the q is measured along the z direction, but from the point where potential is 0 and it downwards. So then my Hamiltonian for this system would be, so h equals p square by twice m minus mgq. And since this is a conservative system, so this would be my total energy E. And if I rewrite the equation, then this will give me, so p square equals 2m times E plus mgq. Okay. Now again, if I take a constant value for this energy E, then I will trace out a curve in the PQ plane. In this case, the curve is a parabola. So as you see, this is an equation of a parabola. So suppose if I take, say, E equals E1, then uh, it will trace out one of the parabolas. So let me say this is my uh, at p equals 0, q should be minus twice m E1. So uh, this one here, uh, like this, suppose. So this is for E1. So E equals E1. And suppose there is another thing with E equals E2. That would be another parabola. If E2 is bigger, then it would be shifted towards the left. So like this. Yeah. So this is E equals E2. Okay. Now, the way I have drawn it, has been implicitly assumed that E2 is greater than E1. Okay. Now, you can draw this actually. Hmm. You can draw this. So, the next thing I want to understand is that is there any general property that when a system evolves along these kind of constant energy, this constant energy contours of the phase space, uh, can we say something about the evolution? Okay. As it matters, we can do it. So first of all, to understand that, let us consider a bunch of particles with momentum. Sorry. Yeah. So let us consider a bunch of particles with momentum between p2 and p1. So consider, say, n number of particles with their momentum enclosed between p1 and p2, and energies between E1 and E2. Okay, I did it in the opposite. So I meant this. So I am assuming P2 is greater than P1. So uh, suppose here is my P2 and here is your P1, let's say. So the particles momentum will be between this. They are distributed in between this thing, and their energies are in between E1 and E2. So the in the phase space, all the particles lie uh, within within this area. Okay, so this is the location of those particles in phase space, and they occupy this area in phase space at t equals 0. So this is at t equals 0. This is the volume of the phase space that those particles occupy. I want to know, after a certain time t, uh, where these bunch of particles will be. So these bunch of particles would be transported somewhere else, okay, according to the Hamilton's equation. Now I know that in this scenario, the Hamilton's equation transports them along the trajectory of the constant energy. Okay, so for example, quite obviously, after time t, this point will be transported somewhere over here, because this will be transported along this line, and this point will be transported somewhere, let's say, along here, which I don't know, let's say. Hmm? and the other points, so this point will go here, and this will go there. So the particles which were enclosed between that orange area will now be shifted to this say white area. So this is uh, at T. Okay. Now, because of this evolution, I want to know what is the relation between these two areas. So the area that the particles occupied in phase space at t equals 0, and the area that the particles now occupy in phase space at time t. All right. So how do we find that? Okay. So the way to find this is quite simple. You have to find out basically the area enclosed between mm, those two lines, those two horizontal lines that I talked about. Okay. So first of all, let us figure out how does my momentum evolves with time, because the thing that was previously at t equals to 0, which was p2, what happens to it uh, after time t? So suppose after time t, uh, p2 becomes p2 prime. So I have to find out the relation between p2 and p2 prime. Okay. But how do I do that? Again, my Hamilton's equation helps me. Okay. So if I find out the evolution of momentum, so p dot is given by minus del h del q, which is nothing but mg, right? So this is my p dot equals mg. So if you solve this equation, then so p at time t will be p at time t equals 0 plus mgt. Quite simple. This is a first order equation, and the solution is quite simple. That means p2 prime will be just p2 plus mgt, and similarly p1 prime will be p1 plus mg times t. Okay. So and remember that once you know the value of p, the value of q can be determined from the conservation of energy, because so p and q are related by this equation. All right. So if you like, and then q as a function of p would be given by uh, let me check. So it would be 1 by mg into e minus p square over twice m. I think so. From that equation, it comes like this. Or maybe I missed a minus sign.
So I think it should be p square by 2m minus.
Yeah. So let me put like this. This is okay, right? My minus e by mg. Yeah, it looks okay to me. Okay. So this is my qp. That is fine. Good. So what is the area then, or what is the volume in this case of the phase space that I am trying to find out here? So let us think about a bit. So this is again your surface integral that you have learned in your perhaps BSc thing. So this the area of this closed thing should be given by, so in general I will call this volume. So volume of the phase space at t equals 0, let's say. So v equals would be this closed surface integration of dp dq. Okay, so basically what you do is you break out these into small pieces, and then you integrate over that, and that is your area. But how do you do it practically? So now you see that the independent variable is p. So p2 and p1 you know, and this q depends on p. So you basically do the integration of the dependent variable before, and you substitute this. So so what you do is that you break this integral into two parts. So integration over dp, and you integrate from p1 to p2, and the integration over dq. So this dq should be the limit should be given by this, but from p1 to p2. All right. So, or rather say e1 to e2. Okay, for a certain p you put it e1 to e2. So what I mean is that, so for people who are not initiated, so the area looks like this. Okay, this is your e1 and this is your e2 surface. So you take an intermediate value of p and you find the area of the thin strip. Okay, so the height of this so-called rectangle is dp. Okay, and the width of this rectangle you have to find. So width of this rectangle, how will you find? You will just substitute this, integrate the value of q here. And what is the value of q here? So sorry, and on the left the value is uh, so q on the left, which I call q2, would be given by rather 1 by mg p square over twice m minus e2, and q1 would be given by 1 by mg p square over twice m minus e1, right? So this is my q1. So these will be your upper limits and lower limits of this integration, right? So once you do this integration, you do the integration over p to cover the whole space. So here now you are integrating from p1 to p2. So that's how you integrate your whole thing. All right. So uh, so this basically gives you integration p1 to p2 dp, and this is dq. Integration of dq means q2 minus q1, and that is given by q2 minus q1 will be given by e1 minus e2 by mg. So this is 1 by mg p1 p2 dp. Perhaps I have made a sign mistake in somewhere. Anyways, so now this e1 and e2 are constant, so you can take them out. Okay, and you get it out as e1 minus e2 into p2 minus p1 divided by mg. So this is your phase space volume at t equals 0. Okay. Now, what will happen if you go to at time t? Okay. So at time t, you will do the same exercise. Remember, so p1, my diagram is not correct, but anyway, so p1 has been transported to say p1 prime, and p2 has been transported to say p2 prime. So basically, it's the same trick. You draw it properly, and so you do the same integration, and you call the last integration to be v prime, and so v prime will be the same. So e1 and e2 doesn't change, remember, because those are the constant energy, but your momentum changes, p2 prime minus p1 prime by mg. But notice the evolution of P is such that P2 prime minus P1 prime is the same as P2 minus P1. Okay. So what I have here is basically the U1 minus E2 is P2 minus P1 by mg, which is equals to my initial volume. Okay. So what I find here is that the density of particles, or rather the density of states, along the evolution of a system of phase space coordinates. Okay. So the density, since the volume remains the same, the density remains the same. So this density of the phase space points along the evolutionary path of the uh, of this phase space trajectory remains constant. Okay, so this is a special case of a general statement called the Liouville's theorem. Okay. And in the next semester, you will be learning a bit more details in a statistical mechanics class. Uh, in my notes also there are some details about the general proof of Liouville's theorem, but I will skip it for this class because I have other plans. Otherwise, I will not complete it within time. All right. So, but note what Liouville's theorem means and what it doesn't mean. So it means that if you evolve a bunch of phase space coordinates according to your Hamilton's equation of motion, the uh, the volume around that phase space coordinate, sorry, so actually the density of particles, so the density of states around that phase space volume does not change. So that means that suppose one phase space point is being evolved from here to here. Okay, then the density of phase space point at t equals 0 around this coordinate would be the same as the density of phase space point around this coordinate at t equals t. That does not mean, however, that at t equals 0, the density of points here and here were the same. Okay. It means that when you evolve that coordinate according to your canonical equations, after time t, the density of points stays the same there. Okay, so you are basically so here you are comparing the density of points at around this at time t with the density of point around this at time t equals 0. So you are not comparing the densities at the same time. Okay, you are just saying that the evolution of density, the time evolution of density remains constant. Okay, so the density doesn't change, it carries always. But at a certain time, so if you take a picture of the whole phase space, that does not mean that the density of points everywhere is the same. So uh, try to remember this subtle difference and do not confuse between what are density of phase space points and what is evolution of the density of phase space points. Okay, so now I will move on to canonical transformation, but before that, let me take some questions if there are at this point.
Sir, this means that the density points of a particular point surrounding a particular point remains constant from time to time, right?
Yes. So if you, so
Okay.
basically if you are imagine if you are sitting on this point and you are following the point wherever it goes, then you will find that the density of points around you remains constant. So it's like a
Okay.
moving train. You are sitting on the roof of the train, and basically the density of point around you basically moves with you. Okay, so the density never changes. Okay.
Okay, sir, understood.
Mhm. Any other questions? All right. So people who are interested in the general proof, there are many excellent textbooks which does that. You can check them. But I will now move to something called the canonical transformation. Okay. So let me start. So let me remind you that from the Lagrangian mechanics, we actually found a very interesting property of the Lagrange's equation, that if Lagrange's equations were valid in one set of coordinate system, then if you define new coordinate systems, then in the new coordinate systems also the Lagrange's equations were valid. What I meant by that is suppose, so I will do it in one dimension uh, to reduce cluttering. Suppose you define a new coordinate system which is a function of the old coordinate and time, and you can basically invert this equation to write uh, that the old coordinates are also function of new coordinates also. Now if you do this transformation, and if Lagrange's equation is satisfied in the old coordinate system, so d dt of del L del Q dot minus del L del Q equals 0, then you can also prove that it directly follows that d dt of del L del capital Q dot minus del L del capital Q equals 0. Now when you proved these things, like many of you did this homework actually, and I noticed that certain steps were like you were using things without proper justification rather, and sometimes those steps might be wrong. Let me give you an example what I mean by that. Okay, and not all of you did that, of course some of you did it. So first let us try to find out, so I have to prove this, right? So all of you did it correctly. So first you tried to evaluate uh, d dt of del L del Q dot. So now if so L is now a function of, so first let me write down that Q is Q of Qt, then Q dot would be del Q del Q times Q dot plus del Q del T, right? Now remember these Q's are function of Q and T only. So these are only Q and T. Okay. So that's why in the next step it follows that if you try to find out del Q dot is equals uh, del Q del Q. Notice the reason why del Q dot and del Q dot is del Q and del Q. It is by the virtue that only this term depends explicitly on Q dot. Okay, and that's why I get del Q dot over del Q dot equals del Q over del Q. It is not because, so if you write this kind of argument, uh, so sometimes you did not uh, write any argument. So this is del of dq dt, and this is del of dq dt, and sometimes I have noticed people somehow they have cancelled this dt and dt and then this del, and somehow it gives them del q, but that is incorrect. Okay, and you would see that it would not work if this was a function of q dot also. Okay, which is it is not, but this will not work. So this is wrong. So don't do that. This is the first. So explain your steps in this way. So if you write q dot, then del q dot over del q dot is del q over del q. That's fine. All right. So then L is a function of L Q, which is a function of Qt, and then a function of Q dot. So Q dot is a function of Q, Q dot, and T. So notice here. So it depends on Q dot also, and in general T, of course. Now you basically try to figure out how will you do it. Okay, so you can do the reverse also. So now basically you have found del L del Q dot. Okay, so if you do the reverse and you want to express this del L del Q dot in terms of del L del small q dot, so you would write that this is del L del small q dot times del q dot del q dot. Okay, something like this. And since this is, again, if you do the inverse of that, you will get the same thing. So this would be given by, if I am not wrong, I hope, del L del q dot times this would be del q over del q. Okay. Again, you have to find out now. You have to find out d dt of del L del q dot. So that by the chain rule would be d dt of del L del q dot into del small q del capital Q plus del L del q dot times d dt of del small q del capital Q. Okay. Now my second comment is about this step. So at this point, many of you basically interchange these operators. So so this d dt of del L del Q, you assume that these two operations commute. So you have written this as del del Q d dt or dq dt. Okay, and you have written it as like del Q dot del Q, something like that, a step like that. But this, I mean, this will hold here, but you have to give proper justification for that. Again, that will come from this. So just try to figure it out. So you cannot just you cannot just interchange these two operations, and these two operations will commute if this dependence, you will figure it's a trivial thing, you'll figure it out yourself. If the dependence is simple like this one, okay, only then. So these are my two small comments, but you did it correctly, and most of you did it correctly. And the message was that if Lagrange's equations were valid in my old coordinate system, then it is also valid in the new coordinate system, and you do not have to rederive Lagrange's equation again and again. You can just write it. Now at this point, we wonder, is it true for Hamilton's equations also? In another word, what I intend to ask is that in Hamilton's equation, there are kind of two explicit variables, P and Q. Okay. So if I define my new P and Q, so suppose I define a new P that is given by and a new Q that is again a function of P, Q and T. And I know that Hamilton's equations were satisfied in terms of old coordinate system. So then if Hamilton's equation is satisfied in the old coordinate system, that means I have P dot equals minus del H del Q and Q dot equals del H del P. Then will it follow that in the new coordinate system also I will have capital P dot equals minus del H del Q and capital Q dot equals del H del P. So it is basically the same question that we asked in the Lagrange case. The same questions we are asking in the context of Hamiltonian. And we want to know that if we make a transformation of this kind, like a coordinate transformation in the phase space, it's basically a phase space coordinate transformation, then if my Hamilton's equations were true in terms of my old coordinates, then will it still be true in terms of the new coordinate system? In Lagrange's equation, we didn't have to worry. Okay. You give me any arbitrary transformation and the Lagrange's equation, the structure of Lagrange's equation stays the same there. But in the case of Hamilton's equation, it will not be true. So this, this is in general not true. Okay. So what it means that if you do any arbitrary transformation like of this nature, then the structure of Hamilton's equation will not hold. So you have to take special care for these transformations so that the structure of Hamilton's equation stays true. So those special transformations under which my structure of Hamilton's equation do not change, that means these things still hold, would be called canonical transformations. Okay, so only those transformations which keeps this structure invariant, so these are canonical transformations. Okay, so I will use this shorthand CT very often. So notice this. So we will find out the condition under which these things hold. Okay, so basically, if you do any arbitrary transformation, then things will not hold. Okay, so the structure of the Hamilton's equation will not stay true. So only those kind of transformation that keeps the structure of the Hamilton's equation invariant will be called my canonical transformations, and that's why canonical transformation will be very important. Okay. Now, so now notice, so one small piece of nomenclature. So notice that for any arbitrary set of P and Q, the Hamilton's equation do not hold. So for those set of P and Q for which the canonical equations of the Hamilton's equation hold would be called canonically conjugate coordinate and momentum. Okay, so when we talk about coordinates and momentum, usually in quantum mechanics and quantum field theory, we implicitly mean that those are canonically conjugate. That means they are connected by this Hamilton's equation. Those P and Q are connected by this Hamilton's equation. So let us try to find the conditions for canonical transformation. Okay. So conditions for okay. So first of all, for this exercise, we will restrict ourselves into discussion where these transformations do not explicitly depend on time. So these are general canonical transformation where it depends on explicitly on time. Rather, we will focus, because the general treatment is a bit complicated. So we will focus only into those, and these are the things which will bother us the most. So it depends on only P and Q, and Q also depends on P and Q. So these are usually called some restricted version of canonical transformation. All right. So what should be the nature of these things such that my structure of the Hamilton's equation stays true? So first of all, I need to find out, I need to write down my Hamilton's equation in a very, say, in a fancy structure. So suppose I define x vector, which is a column vector, which is, say, Q and P. Okay. And y vector, which will rather denote by my new coordinates. So this is capital Q and capital P. Okay. So quite clearly, so I am doing it in one dimension, but the n-dimensional version would be similar. Okay. So x dot would be Q dot P dot, and so on and so forth. You get the idea. So in terms of this x, you can concisely write down the Hamilton's equation as this. So Hamilton's equations will be given by then x dot equals, this is this matrix, which is 0 1 1 so minus 1 0 times x. So if you plug this explicitly, you will readily see that how it gives you the equation. So Q dot P dot becomes 0 1 minus 1 0. Okay. All right. So now you can see that Q dot, oh sorry, it's not x, it's just, I should write it as del h del x. Okay. So so this del h del x is basically, oh, I can write it here. It's del h del q del h del p. Right? Yeah. So Q dot equals del h del p, and P dot is minus del h del q. So it works, right? Now for the n-dimensional version, where you have n number of generalized coordinate and momentum, so this x will be a 2n dimensional column matrix. So for n dimension, so if I have n dimension, then this x matrix is basically then q1 up to qn, and then p1 up to pn. So this is that, and these ones are basically n cross n identity matrix. And that's it. Okay. So you understand that I can write down the Hamilton's equation in a very compact form like this one. Okay. So now I want that my mm, uh, so I want my Hamilton's equation to stay invariant under this equation. By the way, so this matrix, this 1 minus 1 matrix, I will call capital gamma. Okay, so my Hamilton's equation becomes x dot equals say gamma times del h del x. Okay, so this is my Hamilton's equation. Now let us come to that what will happen if I change this thing into if I change my coordinates and momentum. So now basically I have defined y, and y is a function of x, right? Because remember, y is my new coordinates, okay, and the new coordinates were the function of the old coordinates. I can then write down that y is a function of this thing. Then I can write down, suppose I am only focusing on the kth coordinate, then I can write down yk dot, this should be equals del yk del xj dot summation over j. Okay, so it depends on this the coordinates of the old coordinates. So these xj's are the old coordinates, remember. Now again you can write down yk dot equals summation over j del yk del xj. Remember xj dot, since this satisfies my Hamilton's equation, I can extract xj dot from here. Okay, so if I use it, so that will give me xj dot equals gamma j, let's say L, and del h del xl, of course, summation over L. Okay, so what I can write from this, I can write this is summation over jl, xj dot is again gamma jl del h del xl. Okay, again this del h del xl, since xl is a function of all these y's, so you can write this thing here. It should be given by, let me call summation over m del h del ym into del ym del xl. You can do that, right? So now with all these things in place, let us write down this. So summation over jlm, this is del yk del xj times gamma jl. I will write this term first. So this is del ym del xl, and at the end del h del ym. Okay, now notice again, so this del y del x, this matrix, this is the so if you do a coordinate transformation like this matrix is usually called the Jacobian. Okay, So this is kind of the kjth element of a matrix, which I call the Jacobian matrix. So this is my jkj. Okay, it has two indices. This is jkj. Similarly, this is jml, or I will write it in a fancy, in a roundabout way. I will write it as j transpose lm. Okay. So notice what happening here. So this is summation over j, jkj gamma jl, then summation over l also, then j transpose lm. Okay. So I can I can absorb this summation over j and l to write it as summation over m. This is j times gamma times j transpose. The element is the kmth element, and this is del h del ym. Right. This is the idea I got. So I now find out that yk dot equals this times del h del ym dot. But if my Hamilton's equations are satisfied in the units also, that is, if my Hamilton's equations are satisfied in terms of my y coordinates also, so y is my new coordinate, so Hamilton's equations are satisfied in my y coordinates also, then I should be able to write equation in y like this. So if my y coordinate also satisfies Hamilton's equation, then I should be able to write y dot equals gamma times del h del y. That means if I compare it, so this would be yk dot equals summation over m gamma km del h del ym. Okay, so I should be able to write this. But I see that my yk dot turns out to be this times del h del ym. So obviously I will compare, say, apples with apples. This is, so I see that these two equations are strikingly similar if I identify j gamma j transpose with gamma. So if my transformation y to x, so see, this transformation gives you the Jacobian j. So this Jacobian is unique to this transformation. So if the transformation is such that the Jacobian satisfies this relation, which is j gamma j transpose equals gamma, if the transformation is such so that the Jacobian satisfies this relation, then the transformation is said to be canonical. Okay, so this is the condition for canonical transformation. Condition for canonical transformation, and this type of relations are called symplectic relations, and the Jacobian would be called the symplectic Jacobian. So J is said to be symplectic. I think this is the. In fact, in your group theory courses, there is a particular class of group called the symplectic groups, SP series of groups, which basically is related to this transformation. I don't know if you have learned about that or not. Maybe you have learned about SO group, spatial orthogonal, spatial unitary, but there is also a group called symplectic groups. So, in summary, what is the conclusion? So, in Lagrange's equation, any kind of point transformation gives you, like, keeps your Lagrange's equation invariant. In Hamilton's equation, we are not so lucky. If we make a transformation, we have to be careful so that the transformation we are making and the Jacobian that transpire from that transformation, if it is symplectic, then I know that my Hamilton's equation the structure of the Hamilton's equation would be preserved under that kind of transformation. So those transformations would be called canonical transformation. Okay, I guess I will stop at this point. You can ask me questions now. Any questions? All right, then. Hopefully you got the idea. Okay, then I will stop recording now.